In today's video lecture, we're going to start the packet of notes dealing with sinusoidal steady-state analysis. In many ways, this is the most important part of VE 210. So many areas of electrical engineering, signal processing, communications, control systems, power systems rely very heavily on the foundations that we're going to learn in this packet of notes. For those of you who are not going into electrical engineering, a lot of what we learn in this packet of notes will still be important to you because this packet of notes is the beginning of looking at frequency domain analysis, something that is a big part of many different aspects of engineering. Before we start getting into this topic, however, it is very important that you have a solid background in complex numbers. Complex numbers are going to be a big part of this packet of notes. So, if you are not completely adept at using complex numbers, knowing how to go from rectangular to polar coordinates, understanding what complex numbers are, understanding how to plot complex numbers, etc., you should stop this video now and instead watch the review video on complex numbers and sinusoids. That review video will give you all the background review that you need in order to fully understand what is going on in this packet of notes. Once you watch the review video, you can then come back and fully appreciate the important concepts in this packet of notes. Okay, let's get started on sinusoidal steady-state analysis. First off, in the book, this is chapter 9. So specifically, you want to read sections 9.1 to 9.9, skip a couple sections, and then read sections 9.12. So we're going to start this lecture by just briefly talking about what we mean by sinusoidal steady-state analysis. That's covered in section 9.1 and 9.2 of the book. Then we're going to introduce two very important mathematical concepts that is going to make solving these problems doable. Phasors are covered in section 9.3, and impedances and admittances are covered in section 9.4. We will then spend quite a bit of time doing problems that employ both phasors and impedances. And finally, section 9.12 is dealing with phasor diagrams, a relatively minor visual topic that goes along with sinusoidal steady-state analysis. As I said at the outset of this lecture, we're going to begin looking at thinking in the frequency domain. So we're going to begin thinking in the frequency domain in this set of notes. And for many of us, the rest of your career in engineering, you'll be thinking in the frequency domain an awful lot. Let's get started. So let's think about where we've been so far. When we started introducing RLC circuits a couple note packets ago, we first talked about DC steady-state analysis. This was covered in chapter 6 of the book. The idea behind DC steady-state analysis is if the input is a constant function, constant voltages, constant currents, what we call direct current, if that is applied to an RLC circuit, the output is also going to be DC. Remember, these outputs can be voltages or currents, it doesn't matter, but the bottom line is the output follows the same form as the input. If the input is DC, the output is going to be DC. And the way we found that DC output is we replaced every capacitor by an open circuit and we replaced every inductor by a short circuit. In chapter 7 and 8 then, we took this a step further. We looked at transient analysis. We still had RLC circuits, but now instead of the input being a constant DC source, the input was a changing DC source. By change, we mean perhaps that we're turning the source on at time 0, or maybe we're turning the source off at 0, or at time 0 we're changing the source from 1 volt to 2 volt, or maybe we're adding a resistor that's going to change the circuit. But the bottom line is at some time t0, usually 0, we're making a fundamental change in the circuit, and basically what's going to happen is the circuit wants to reattain DC steady state. It starts from one DC steady state value and wants to adjust to another DC steady state value. And what's going to happen is the output is going to include a transient response, and this is the circuit's attempt to reattain DC steady state. So the output in cases like this is we still had a DC steady state output, plus we had a transient response. And of course, the transient response, if it's first order, is always a decaying exponential. If it's second order, it could be two decaying exponentials or a decaying sinusoid, or in the case of critically damped, a decaying exponential plus a decaying exponential multiplied by t. But the important thing here is the forced response. This is the part that exists after the transients die down, is still of the same form of the input, and that was DC. If your inputs are constant voltage sources or current sources, every output, every voltage, every current you measure at the output will eventually be a constant value as well. But what happens if the input signal is not DC, but is a sinusoid? That is giving us what we call sinusoidal steady state analysis, SSS analysis, which we also call AC analysis. AC, of course, stands for alternating current. This is a little bit of a misnomer because very often, in fact, more often than talking about currents, we're talking about voltages. But we still call it alternating current even if we're talking about voltages. The bottom line is sinusoidal steady state analysis is dealing with circuits where inputs are going to be sinusoids. What happens is the differential equations we get look just like what they did before. For example, second order, you get x double prime plus ax prime plus bx is equal to something on the right. But now there's something on the right, rather than being 0, which was what we got in the source-free case, or a constant, which is what we got in the driven case before, the right-hand side is now a sinusoid. So continuing, what we see then is if the input is a sinusoid with an amplitude A, a frequency omega naught, and a phase angle theta, if you pass that through an RLC circuit of whatever complexity you want, the output is going to be a sinusoid of the same frequency, but it's going to have a different amplitude and a different phase. So an input amplitude of A is going to give you an output amplitude of B. An input angle of theta is going to give you an output angle of phi, but the frequency is the same. So just like in the DC case, a DC input ultimately gave you a DC output, an AC input ultimately gives you an AC output. I should point out here that we are going to have transients, just like we did in the DC case, but we're going to ignore them. We're really concerned about the sinusoidal steady state response. We're not concerned about the transient response at this point. And one of the big results we're going to see is that the values for the amplitude and the phase of the output, voltage or current, whatever we're measuring, is going to depend upon the frequency of the input. Once again, we're going to have circuits that are frequency dependent. We saw this a little bit earlier with the Baxendale tone control circuit, for example. But before we look at it just from a very basic level, now we are going to look at it in detail from a very mathematical level. So before we get into actual doing the math, let's discuss a little bit why this is important. Why is sinusoidal steady state analysis important? Well, for a couple reasons. First off, if you've taken a math course where you've learned about the Fourier theorem, you probably saw that any periodic function can be decomposed into a sum of harmonically related sinusoids. So for example, a square wave or a triangle wave of frequency 100 Hertz can be written as sinusoids of multiples of 100 Hertz, 100 Hertz, 200 Hertz, 300 Hertz, 400 Hertz, etc. It goes beyond square waves and triangle waves, however. Any periodic waveform. For example, you might have a waveform that looks like this. I'll try to recreate that shape of the wave. So basically, here's your waveform and then it repeats, so it becomes periodic. Any periodic waveform you could break down into a sum of harmonically related sinusoids. So for example, if this waveform here repeated 100 times a second, we could model it mathematically as a 100 Hertz sine wave plus a 200 Hertz sine wave plus a 300 Hertz sine wave plus a 400 Hertz sine wave, etc. And the 100, 200, 300 Hertz sine waves are what we call harmonics of each other. When you take courses like EE 350 and 353, you will study the Fourier theorem and some of its applications in detail. At this point, we really just need to appreciate the fact that many different types of signals, voice signals, music signals, other types of communication signals, can be modeled as sums of sinusoids through this Fourier theorem. For this reason, doing sinusoidal steady-state analysis is important. Another reason why it's important: our power system is not a DC power system. The signal coming out of our outlets is not a constant DC voltage. It is a sinusoidal voltage. And so because our power systems use AC signals, it's important to understand how circuits will be affected by those. Once again, sinusoidal steady-state analysis. Thirdly, and this is actually closely related to the first bullet point, is that we already saw that some circuits are going to be frequency dependent, the Baxendal tone control circuit, integrators and differentiator circuits, etc. So sinusoidal steady-state analysis allows us to see how these circuits operate at different operating frequencies. So circuits such as equalizers. An equalizer is a circuit that is used to make sure that the different frequency components of an input signal are each amplified by the right amount. A frequency selective filter is a circuit that will allow certain frequencies to pass through to the output but not allow other frequencies to pass through. This is really important in communication systems. Speaking of communication systems, modeling communication systems and channels is important, and what we see is that these communication channels themselves are often frequency dependent. So when a communication signal goes through a channel, whether it's a coaxial cable or whether it's the air or whether it's a fiber optic cable or something like that, the different frequencies present in that signal might be affected different ways, and so we say the communication channel is frequency dependent. To understand that frequency dependency, we need sinusoidal steady-state analysis. So bottom line is there are many different applications, not just in electrical engineering, but in mechanical engineering, aerospace engineering, computer engineering, biomedical engineering. There are many different types of engineering where understanding sinusoidal steady-state analysis or AC analysis is critically important. So this is why we're going to be spending a lot of time on this very important topic. We're going to start with an example that on the surface looks very straightforward. It's a simple single loop RLC circuit. We are going to see that the solution of this problem is actually extremely complicated if we don't use shortcuts. So bear with me as I go through the problem on this page. It is going to look extremely complicated. Do not worry about it because I assure you we will come up with a much easier way of doing this problem. But I want to do it this difficult way first to show how important it is to come up with good mathematical shortcuts. So bear with me on this. You will not have to solve circuits this way, I assure you, but I'm doing it once to show you why it's important to come up with shortcuts. Okay, before we get into solving the circuit, I do want to remind you of two important trig identities. Sine of A plus B, you can always write as sine A times cosine B plus cosine A times sine B. Likewise, cosine of A plus B is equal to cosine A times cosine B minus sine A times sine B. We will use both of these trig identities as you'll see in a minute. Okay, so here we have a series RLC circuit. So we have a capacitor, a resistor, an inductor, powered by a voltage source. The voltage source is a sinusoid with an amplitude of 10, a phase angle of 0, there's no theta term, and a frequency of 4 radians per second. What we know from sinusoidal steady-state analysis is every voltage and current in this circuit, once the transients are gone, is going to be a sinusoid of frequency 4 radians per second. So this loop current, I of t, we're going to say it has some amplitude I that we do not know. It's going to have a phase phi that we do not know. But we do know its frequency has to be the same as the frequency of the sinusoidal input. Input is 4 radians per second. The current, our output, is going to be 4 radians per second. If this were a DC problem, and the capacitor and the inductor were both resistors, this would be a trivial problem. Imagine this was a DC source of 10 volts, and we had resistances of 3 ohms, 5 ohms, and 2 ohms. 10 volts divided by 10 ohms, Ohm's law, the current would be 1 amp. But because we have a capacitor and an inductor, and because the input is sinusoid, we're going to see that it is much more complicated. So what we need to do to solve the circuit, we need to find out what the amplitude of that current is and what the phase angle is going to be. So once again, bear with me, this math is going to be really long and complicated, just a warning. So let's do KVL. Let's start at this point, go through a voltage source, voltage drop across the capacitor, across the resistor, across the inductor, and end up at the starting point. So from KVL, we know that minus Vs of t plus Vc of t plus Vr of t plus Vl of t is equal to 0. Because we're ultimately looking for the current, let's try to get I of t in this equation as much as possible. So we get minus Vs of t, you can't do anything with that. Remember the voltage across the capacitor, you can re-express as the integral of the current through the capacitor. So we can rewrite that as 1 over c times the integral of I of t dt. The voltage across the resistor, from Ohm's law, we know is a resistance times the current through the resistor. And the voltage across the inductor, from the VI characteristics of an inductor, is just L times the derivative of the current. And this is still going to equal 0. So now let's plug in the expression for Vs here, and let's plug in this thing we're solving for, I of t, into here, here, and here, and see what we get. So we get minus 10 cosine of 4t plus 1 over c, c is 0.25 farads, so it's going to be 4, times the integral of I dt, but I of t is I cosine of 4t plus phi dt. R times I of t is going to be 3 times I cosine of 4t plus phi. Plus L dIL dt, L is 0.5 Henry, times the derivative of I cosine 4t plus phi. And once again, all of that is going to equal 0. So let's do this integration and this differentiation. First term doesn't change at all. The integral of cosine of 4t plus phi is going to be 1 over 4 times the sine of 4t plus phi. So this becomes 4 times 1 over 4 times I sine 4t plus phi. This term doesn't change at all. The derivative of a cosine is a negative sign, and once again that frequency 4 comes out. So it's going to be plus 0.5 times minus 4I sine 4t plus phi. And all that equals 0. So in other words, the integral becomes that, the derivative becomes that. Next thing we see is that this term and this term are both sines, so we can combine them. So we now get that minus 10 cosine of 4t. Now we had plus I sine of 4t plus phi minus 2I sine of 4t plus phi. Putting those together, we get minus I sine of 4t plus phi plus 3I cosine 4t plus phi equals 0. Now we're going to use these two trig identities here. First term unchanged, minus I sine of 4t plus phi is sine of 4t cosine of phi plus cosine of 4t times sine of phi. So it's sine of 4t cosine of phi plus cosine of 4t times sine of phi. 3i cosine of 4t plus phi becomes 3i. Cosine of a plus b is cosine a cosine b minus sine a sine b. So this becomes cosine of 4t cosine of phi minus sine of 4t sine of phi. And once again, all that equals 0. What we see now is that we have some cosines of 4t's, and we have some terms that are sine of 4t. So let's group those together. So we get cosine of 4t times minus 10, that's that term, minus I sine of phi, that's this term, plus 3i cosine of phi, that's this term. Plus sine of 4t times minus I cosine of phi minus 3i sine of phi. And all of that equals 0. So all that we're doing here is combining the cosine of 4t terms together and grouping the sine of 4t terms together. For this whole expression to equal 0, what this means is that these two things in brackets must both be equal to 0. Because cosine of 4t certainly is not always 0, and sine of 4t is certainly not always equal to 0. So the only way this expression can be equal to 0 is if this thing equals 0 and this thing equals 0. So let's look at this second one first. Bringing the 3i sine of phi to the other side, we see that 3i sine of phi has to equal minus I cosine of phi, which in turn is saying that sine of phi over cosine of phi is equal to minus 1/3. But sine of phi over cosine of phi is tangent of phi, so tangent of phi is minus 1/3. Solving for phi, we get phi is the inverse tangent of minus 1/3, or negative 18.4 degrees. So let's solve this left bracket now. We know that 3i times the cosine of phi, which we now know is minus 18.4 degrees, minus I times sine of phi, once again we know what phi is, equals 10. This becomes 2.85 times I plus 0.32 times I is equal to 10. Solving for I, you get I is equal to 3.16. So we can put everything together, and we see that if we take this 10 cosine of 4t and drive this capacitor, resistor, inductor series combination, the resulting current is I of t is 3.16 cosine of 4t minus 18.4 degrees amps. We did all that work just to determine what the amplitude of the current is and the phase angle of the current. So look at this page. Look at all the trig we had to do just to find two simple parameters: the amplitude of the sinusoid and the phase angle of the sinusoid. Imagine how complicated it would be if you had multiple voltage sources or had some current sources in there. Or what if you had capacitors, resistors, and inductors that were not necessarily in series? You had a more complicated circuit. Obviously, trying to solve a circuit like this using just the differential equation is very burdensome. We need to come up with a shortcut. So once again, don't worry about what we actually did on this page, other than to realize that we don't want to have to solve circuits this way. What if I were to tell you that we are going to come up with an algorithm that basically makes this circuit no more difficult than this circuit? If you were given this, you'd be jumping for joy with how easy it is. 10 volts divided by 10 ohms, you get 1 amp. Well, guess what? We are going to come up with a technique for solving circuits like this here that will reduce to math that's only a little bit more complicated than doing something like this. And that is by using two different concepts, something called phasors and something else called impedances. So once again, what we desire is to have a solution method where we did not have to write differential equations at all. Differential equations add complexity. Well, what we're going to see is that by using two concepts, phasors and impedances, which we will learn now, that will yield entirely algebraic models from which we can find the sinusoidal steady state response. There's only one catch, and that catch is we're going to have to use complex numbers. Way back in high school, you've probably learned about complex numbers, the square root of -1, I, which we now call j, and you probably wondered at the time, when am I ever going to have to use complex numbers? Well, we used complex numbers a very little bit when we talked about transient analysis, specifically when we looked at underdamped responses because the roots were complex conjugates of each other. But even then, the use of complex numbers was very minimal. Now we're going to use complex numbers extensively. We're going to use it with both voltage and current sources. That's what the phasor concept is going to provide. And we're going to use it with capacitors and inductors. And that's what the impedance concept is going to be. So basically, the phasor concept, which we'll talk about in more details in the coming slides, it's just a shorthand notation for representing a sinusoid using a complex number in polar form. A complex number you might have in rectangular form, something like 4 plus j3. You can re-express that complex number in exponential form, and that would be 5e to the j, and then you get an angle in radians, which is 0.644. And there's a third way that you can now designate this complex number. It's called polar form. It has a magnitude of 5 at an angle of 0.644 radians, or we often like using angles in degrees, and that would be 36.9 degrees. So we're going to utilize this concept here by whenever we see a sinusoid of a form a cosine omega t plus phi, we're going to re-express it as a at an angle of phi. This is just a polar form of a complex number. The idea here is there are three important pieces of information in the sinusoid. There's the magnitude, there's a frequency of operation, and there's the phase. The complex number in polar form allows us to keep track of two of those three. Notice the omega doesn't show up at all in this complex number. However, as we saw from the previous couple pages, the frequencies are going to be consistent throughout the problem anyway. So we're going to see that we can actually remove that frequency from consideration and just put it back in at the end. So the bottom line is the phasor, as we'll see in the next couple slides, it gives us a shorthand notation for expressing a sinusoidal voltage or current. The impedance concept, which we'll once again discuss in a few slides from now, it's based upon a generalization of Ohm's law. The idea behind the impedance concept, however, is to replace the capacitor and replace the inductor by a resistance, and I'm going to use air quotes here, by a resistance so that you can use more resistive types of equations. But the wrinkle here is that the resistance is going to be a complex resistance. Wherever we see a capacitor, we're going to replace it with a resistance of a minus j over omega c. Wherever we see an inductor, we're going to replace it by a resistance of j times omega L. So rather than having resistors with values of 10 ohms or 20 ohms or 30 ohms, you're going to have capacitors of value minus j 10 ohms, minus j 20 ohms, minus j 30 ohms. And you will have an inductors of value plus j 10 ohms, plus j 20 ohms, plus j 30 ohms. So once again, we haven't gotten there yet. We'll get there in a few slides. But the bottom line is phasors are going to use complex numbers in polar form, and impedances are going to use complex numbers in rectangular form. So final comment on this slide is although phasors and impedances are both going to use complex numbers, we associate phasors with voltage and current sources and voltage and current variables. So phasors are associated with sources and variables. Impedances are also going to be complex numbers, but they're associated with capacitors and inductors. Technically resistors too, but a resistor's impedance is the same as its resistance, as we're going to see very soon. On the previous page, we introduced the concept of phasors, where you use complex numbers as a shorthand notation for keeping track of the magnitude and phase of a sinusoidal signal. Let's develop this formally on this page and then look at some of the properties of phasors to see why they're actually useful. So we have a function, f of t, f cosine omega t plus phi. The way we develop the phasor is we start by adding an imaginary component, j f sine omega t plus phi. The next thing we're going to do is utilize Euler's identity, remembering e to the jx is cosine x plus j sine x. So this thing here now becomes e to the j omega t plus phi times f. We can then utilize the fact that e to the a plus b is equal to e to the a times e to the b to break the complex exponential that way. The next thing we're going to do is we're going to suppress this e to the j omega t term. Because that frequency term is going to be present in every voltage and current in the circuit, we're going to ignore this. We're also going to ignore the fact that we're only looking at the real part of this f cosine omega t plus phi plus j f sine omega t plus phi. And so what we're left with is f e to the j phi, which is a complex number in exponential form, or the way we like to write it, f at an angle of phi, which is a complex number in polar form. So although technically every time you create a phasor, you're doing these steps of adding the imaginary component, using Euler's identity, suppressing the e to the j omega t term, suppressing the real part, and expressing it as a complex number in polar form, in practice, you really can go directly from the time domain to the phasor domain. Specifically, if f of t is written as a cosine, f cosine omega t plus phi, you can immediately read off the magnitude, and that becomes the magnitude of the complex number, and then the phase becomes the phase of the complex number. And we use this notation here with the tilde to represent that it is a phasor. So the bottom line, if you are converting a sinusoidal signal that's already in cosine form to its phasor equivalent, you can do it from inspection. F of t equal 5 cosine 100t plus 45 degrees. F tilde is just 5 at an angle of 45 degrees. Really no work involved at all. We're suppressing the fact that the frequency is 100 radians per second because we don't need that right now. What happens if you have a minus sign out front? Well, here you use the fact that minus cosine of x can be written as cosine of x minus 180 degrees. So if you have a negative sign, all that you do is subtract 180 degrees from the phase before you make the phasor. So in this case, f tilde is 5 at an angle of 45 degrees minus 180 degrees, or 5 at minus 135 degrees. I should point out that you could also add 180 degrees. It gives you the same thing. So we could instead write that as 5 at an angle of 225 degrees. So that's what you do if it is a cosine. If it's a positive cosine, you get it directly. If it's a negative cosine, you do have to take into account the negative sign with a 180 degree phase shift. But what if you have a sine? There are two ways to handle sines. The first way is to recognize the fact that sine of x is just cosine of x minus 90 degrees. So if your time domain function is written in sine form rather than cosine form, all that you need to do is subtract 90 degrees from the phase angle before you create the phasor. So for example, if f of t is 3 sine at plus 110 degrees, that's the same as 3 cosine at plus 20 degrees, so the phasor is f is 3 at an angle of 20 degrees. However, there is a second way that you can deal with sines. I'll show that down here. We said that a sine is just a cosine with a 90 degree phase shift. 90 degrees is the same as pi over 2. So then we get this expression on the right here, but then remember that e to the a plus b is e to the a times e to the b, and so the e to the j minus pi over 2 can come out. There's another important property of complex numbers. E to the minus j pi over 2 from Euler's identity is cosine of minus pi over 2 plus j sine minus pi over 2. Minus pi over 2 is the same as minus 90 degrees. Cosine of minus 90 degrees is 0. Sine of minus 90 degrees is negative 1. So we get this important property, e to the minus j pi over 2 is the same as minus j. So that gives us that. This gives us this alternate way to deal with sines. If you have a time domain function as a sine rather than a cosine, rather than subtracting 90 degrees from the phase angle, you can keep the phase angle as is and just put a minus j out front. In other words, subtracting 90 degrees from the phase is the same as multiplying by negative j. Which means that 3 sine at plus 110 degrees, rather than writing it as 3 at an angle of 20 degrees, we could write it as f as minus j3 at an angle of 110 degrees. So once again, you have two options when you have a sine. One, subtract 90 degrees from the phase before you create the phasor. The other thing you could do is leave the angle as is, but put a minus j out front. This expression and this expression are identical. In some cases, we might find this more useful. In other cases, we may find that more useful. So why are these phasors useful? Well, as I said before, they're useful because it allows us to use one complex number to store two pieces of information, the magnitude and the phase. But there's another advantage as well. Let's look at differentiation and integration in the time domain and see how they transform in the phasor domain. So think about a cosine function in the time domain. When you take its derivative, what happens? The derivative of cosine is negative sine, so you get a negative out front, and it becomes a sine. Furthermore, this frequency shows up out front in the magnitude. But this part of it, you can express in phasor form. Remember, if it's a sine, one thing you can do is just do minus j times f phasor. So we get that expression here, and then these two minuses cancel. We get just j omega f phasor, and we get our one important result. Differentiation in the time domain is the same as just multiplying by j omega in the phasor domain. Integration, we get a similar property. So once again, f of t is f cosine omega t plus phi, and it has a phasor like that. When we take the integral in the time domain, the integral of cosine becomes positive sine, but this omega frequency shows up out front in the denominator. Once again, we know from the previous page that f sine omega t plus phi you could write as minus j f phasor. So now we get minus j over omega times the phasor. Then we have another important property. What does minus j equal? Let's multiply it by j over j, so we're multiplying it by 1. We get negative j squared over j. But what's j squared? It's negative 1. So we get negative 1 over j, or 1 over j. And we get an important property of complex numbers. Minus j is the same as 1 over j. So this minus j in the numerator, we can write as a positive j in the denominator, and we end up with this second important property, and that is that integration in the time domain is the same as dividing by j omega in the frequency domain. So the two important results here, as we'll see on the next page in an example, differentiating in the time domain is multiplying it by j omega in the phasor domain. Integrating in the time domain is dividing by j omega in the phasor domain. So let's revisit this problem we looked at before. So if you go back a few pages, you saw that we had this integral differential equation representing the KVL voltage drops for the circuit. Let's convert everything to its phasor equivalent. First off, this time domain signal Vs of t has a phasor value of what? From inspection, because it's a cosine already, it's just 10 at an angle of 0 degrees. Notice the fact it's 4 radians per second doesn't show up at all in that phasor. How about our variable I of t? It's a variable, so it remains a variable, but it's now a phasor variable. We're just going to call it capital I tilde. So now let's take this expression here and convert each of these terms to its phasor equivalent. Minus 10 cosine of t is just minus 10 at an angle of 0. 4 times the integral of the current. Remember, integration in the time domain is the same as dividing by j omega in the phasor domain. So this becomes plus 4 I tilde over j4. Where does this 4 come from? That is the frequency that we're operating at. So instead of integrating, we're now dividing it by j4. This term's pretty easy. 3 I cosine of 4t plus v in the phasor domain is just 3 times I tilde. How about the differentiation? 0.5 times the derivative of I of t becomes 0.5 times j omega times I tilde. Once again, this 4 is a frequency of operation. So what we see is we've taken the integration, turned it into a division by j4, and we took this differentiation and turned it into a multiplication by j4. But why is that useful? We can now solve for I tilde. I tilde, first term, 4 over j4 is just 1 over j, which is negative j. This 3I tilde just becomes a 3. This 0.5 times j4 I tilde just becomes j2 times I tilde. So this equals 10 at an angle of 0 degrees. So we get I tilde times 3 plus j1 equals 10 at an angle of 0 degrees. Solving for I tilde is 10 at an angle of 0 degrees divided by 3 plus j1. So how can you evaluate this expression for I tilde? One way is just plug it into your calculator if you have a calculator that can do complex numbers. If you don't have that, you can convert the complex number in rectangular form to a complex number in polar form. 3 plus j1 is the square root of 10 at an angle of 18.4 degrees. And then if you remember the properties of complex numbers, when you divide complex numbers in polar form, you divide the magnitudes and you subtract the angles. So the result of this division is 10 divided by the square root of 10, which is the square root of 10, at an angle of 0 minus 18.4 degrees or negative 18.4 degrees. Once again, if you have a calculator that can do complex numbers, you can get this directly. We're not quite done yet because we were not asked to find I tilde, we were asked to find I of t. But the last step is trivial. To go back from the phasor domain to the time domain, so convert back to time domain, all that you need to do is you take the magnitude of the complex number, that becomes the magnitude, times the cosine of omega t, we know omega was 4, plus the phase angle, which is negative 18.4 degrees. And this becomes our I of t. And of course, square root of 10 is 3.16. We get the same answer here that we had after a page of doing trig identities. 3.16 minus 18.4 degrees. (3.16 minus 18.4 degrees). And the only math we really had to do was this math here. Next lecture, we're going to introduce the concept of impedances, which will make this problem even easier, because it would allow us to totally get rid of the integration and the differentiation. And once we combine phasors and impedances together, we will really see the advantages of working in the phasor domain for sinusoidal steady-state analysis. Have a good day.